Okay. So, okay, hi everyone. We are very happy to have JianWei Qiu today from Jefferson Lab. Uh, JianWei really doesn't need an introduction. Everybody knows him. So let's just get right away to hear from his exciting talk. Today, he's going to tell us about exclusive hard processes for extracting GPDs. Thanks, JianWei, for agreeing to give this talk. And when you're ready, please share your screen.
Okay.
And we are ready to listen to your seminar.
Thank you. First of all, I'd really like to thank the invitation. Unfortunately, I could not be there in person. I really wish I could, because interaction in person, it really make a difference. But I will try to convey the message as clear as I can. Then I'm going to turn off my video before, so in that case, make sure in between the connection is better. Can you see my screen?
Yes.
Yes.
Okay. Thanks again for inviting me. Today, I'm going to tell you some new work I did with a collaborator from Michigan State. Then the title is Exclusive Hot Process for Extracting GPDs. I will try to first tell you why GPD is very important. Then I'll tell you more about the process from which we can extract the GPD in great details. So then we know the nucleons, the hadrons, are fundamental building blocks of all atomic nuclei, but nucleon is not elementary. Nucleon is a strongly interacting, relatively bound state of quarks and gluons. That our understanding of nucleon has been evolving. This, I'm sure will continue to evolve. Then because the QCD is in some sense very unique due to its non-abelian nature or color confinement. So we have a elementary degree freedom, the quarks and gluon, but at the same time, we have a hadron, the emerging phenomena of this strong interacting physics. So we have say, for example, nucleon has a mass, which is the energy of the nucleon when the nucleon is at rest. Because it's very well defined in QCD, because you have a Hamiltonian, you sandwich it between the nucleon state, normalized, you get a mass. If the nucleon is at rest. Similarly, you have a spin nucleon that's creating the angular momentum of the nucleon when it's at rest. So it sounds very simple, well-defined, but unfortunately, to understand this is the Fourier is still beyond the best mind we have. Because we do know the Hamiltonian, we do know the Lagrangian, but we don't know the state. So then how can we extract this information from the measurement? So then the QCD, as I mentioned earlier, has two very unique features in the region where your momentum transfer is very large. You're in the asymptotic region. In that case, perturbed QCD is has been proved to be successful, has been working beautifully for the energy region when the momentum transfer much larger than 2 GeV, that corresponding to distance scale much less than 1/10 of a Fermi. But however, most rich and interesting physics of the strong interaction physics, strong interactions in the other region, from 0.1 to about 10 Fermi, which is corresponding size of the largest nucleus. So in that case, this is the region I often called the QCD at the Fermi scale, is probably the most interesting, rich, complex region of the theory. All the emerging phenomena depend on the scale at which we try to probe them. So if I mentioned earlier, perturbation theory has been very successful to calculate the phenomena at this very short distance. But that kind of probe at the very short distance is not very sensitive to the detail of the hadronic structures for the physics at the Fermi scales. So what can we do? So well, in the last decade or more, we have been developing a new type of observable. The observable requires two distinctive scales. Then you like to have a hot scale to localize the probe to see really the particle nature of the quarks gluon, in the sense that quarks gluon is defined at a short distance scales. Then also you need same time, you have your observable also sensitive to a soft scale. That scale to be more sensitive to the emerging region of the hadron structure. It can be cover the region about the order of a Fermi. So that's exactly the observable will pay a lot of attention last decade or more. Then this is also related to our effort to build a future EIC, because when you have lepton hadron collider, the two-scale observable is very natural observable in this environment. So then there's a two type things I'm going to talk about it. One is say, how can we see the internal structure of the hadron that without see quarks gluon, because we never see quarks gluon in isolation. So then the two situations when I try to discuss here, first is, as we learned from more than 100 years, if you want to see something, a small internal structure, you break that. So then the problem is in this theory, QCD, if the nucleon is broken, like a semi-QDS example, I have a proton, have a lepton collide by exchange, large momentum transfer. I break the proton, then interact with the quark, the gluon inside the proton. Then eventually the quarks gluon will be emerge back to the hadron, could be the pion, kaon, or nucleon, all these things. But during that process, I actually trigger a lot of radiation because I feed so much energy into the collision, then a lot of radiation. So imagine the quark, for example, a parton, I probed at the collision point. The parton could have a longitudinal momentum as well as the transverse momentum, but that transverse momentum at the point of the collision is not the typical transverse momentum of the parton inside, say, proton wave functions. If you want to really understand the hadron structure, how the parton can find motion inside the bound proton, it's difficult. You have to understand the transition from the non-perturbativity to the hard scale, that involving sometimes, most of the time involving the non-perturbative physics as well as the perturbative physics. So then a quick estimate, you can easily convince yourself that the typical broadening of the transverse momentum parton, imagine you start with the order of lambda QCD, one of the Fermi inside a confined system. Because the shower dominates, say, double logarithm with the log S is the collision energy, the scale you probe, you can see that with the energy we have these days and the scale we probe, you can easily make the delta, the transverse momentum broadening over the GeV. So in that case, that means that the physics in the confined system compared to the physics you probe at the short distance are not exactly the same. And also, especially some of the correlation will be diluted. So in the sense, structure information is diluted by the collision-induced showers. So that's the situation for the experiment, if we break the protons. So in this talk, I will concentrate on the second situations. Say, what if we try to explore the structure without breaking it? Then we know we have done these for years. Even the beginning, first thing to discover the proton is not point-like, the internal structure is through the measurement of form factors, through the exclusive process. Then by measuring that, you can have, if you have a exclusive, elastic electromagnetic form factor, you can extract the proton radius in terms of electromagnetic charge distributions. But the same method doesn't work for the color part, because the color gluon itself carry the color, so there is no elastic color form factors. Once the proton absorbed a gluon, the proton cannot be proton anymore. So what happened is that has been discussed, major development in, almost a quarter of a century, more than 25 years ago. Then say, well, we can actually, instead of study the elastic form factor, we study the density of the quarks by exchange a quark and a quark pair, or by exchange of the two gluons through the probe. In that case, you exchange a color singlet system, whether it's a QQ bar or GRU or multi-parton state, but it's a color singlet. If you do that, you have a new type of the form factor for the quark gluon densities. If you imagine the QQ bar is related to quark densities. So in that case, then come to the new concept about the physics called generalized parton distributions. That means the moment you have a proton coming in, you have a scattered but exclusively go to the proton with different momentum by exchange a state which has 0 color. Then in that case, then you can have a QQ bond or glu-glu. Then depend on whether it's a proton to proton. Also, sometimes we have a proton to neutron. You can have a transition form factor as well. But most important part is that you can have a exclusive process to be sensitive to the density of a parton inside the proton. Then the problem is, say, when we exchange, say proton to vacuum quantum number, there is no guarantee you only exchange a quark antiquark pair. You can have exchange a quark antiquark pair plus any number of gluons, so long as they have the same quantum number, then they all contribute to your cross sections. So that's the good part, and that's also a challenger part, right? So then, well, we have a development in the last number of years, and we find that we can actually have factorization. But before I talk about factorization, first let me explain. Say when you exchange, say for example, quark anti-quark, it's a matrix element of 2 fields with gauging invariant and gauging link. So you can actually decompose them into scalar function in a form factor way. Then those scalar functions known as generalized Parton distributions. Then this depends, F and F tilde depend on what the operator is sandwiched between the hadron state, whether you have a vector or this axial vector operators. So you have a H function and E functions. Then and also because you only measure scalar momentum, the P prime, but you don't really know exact momentum change floating between these quark anti-quark if the probe is localized. In that case, because the relative momentum of flow compared to the momentum going into the hard part, you can have a multiple sort of regions. One region is when the both quark anti-quark has the plus momentum moving to the hard collisions, or there's one parton has momentum go in, another parton momentum come out, known as DGLAB region. This all depends on how we factorize the observable to these distributions. So once you open up this to look at the generalized Parton distributions, it seems you have a lot of information you can learn about the hadron structures. But actually more than that, the GPD can tell us even more. Then because we know when we talk especially emerging phenomena, the mass or the spin, they all relate to in some sense, the energy momentum tensor of the theory, which is known. Then if you sandwich the energy momentum tensor between the proton, say, the scalar proton state, you can get this decomposition, you get different form factors. In that case, you will find that the GPD actually directly relate to these form factor, there's a form factor can be related to the mass. Some of them can be related to the pressure distribution or stress force. All these interesting things, we talk about it from emerging phenomena, but they all connected to form factor as well as the spin related to angular momentum, right? The angular momentum of to the proton spin can be related to the moment of the GPD as well. So you can see, knowing all these GPDs as a function of X and a Cassidy T, you can learn a lot of things about the proton internal structures without break the protons. Then in that case, because of some of the interesting, like a moment, gravitational form factor or the other angular momentum, they all relate to different moments of the GPDs. So in order to calculate predict the moment, then you like to know, have good knowledge of the X dependence of GPDs, which is the relative momentum between 2 active partons you transfer between the diffractive hadron and the hard collisions. So that X dependence, if you know it by taking different moment, you can actually make a prediction on these form factors. And in addition to that, then if you, as we all know, if you do Fourier transform as a transverse momentum transfer of this diffractive proton to the position space, you can actually get the special distribution of the probability to find a quark, the gluons. In that case, you imagine you have, as a model predicted by Matthias Burkhardt, say if you look at a proton, the probability to find the proton a parton, a quark, say, inside the proton as a function of the transfer of the position from center at the different value of x. When the x is larger, you expect the proton, pull up the very small configuration from the proton. You expect the special spread of the proton is small, but when the x go to small, then you will expect the proton look more distributed more bigger. But the question is, it's not just the nice pictures. You can ask very good questions in the sense you like to know because how this is, say, imagined when you go to the large position space B, how this distribution falls. That is exactly controlled by QCD dynamics. And also how fast they fall, whether it's exponential fall or Gaussian fall, all these fall, they also depend on the QCD. It's a really QCD dynamics. And also if you know the special distribution as a position space, then you might define the effective radius of, say, quark distribution as a function of x, effective radius of gluon distribution of the function, gluon, it's a proton, in some sense, effective radius of the proton in terms its quark density distribution or in terms its gluon density distributions. If you can do that, we can ask even more fundamental questions. Say, should the effective radius of the proton in terms of its quark distribution bigger or smaller than in terms of its gluon distribution? That completely will impact how the confining mechanism will work. And also, especially when we're interested in small x, where you have a long wave feature of these partonic dynamics, you like to see when the x is going to 0, should the radius, effective radius of the gluon be saturated, or they cannot be go to infinity, right? They eventually will die away. How fast they die away, then in terms of density, all these questions are directly related to the QCD dynamics. And also, it will not be diluted by the, the collision-induced shower because you did not break the proton. So that means this exclusive process is very important, that very powerful, but at the same time, you like to ask and say, can we do that? Because you like to have a larger momentum transfer. You have multi-GeV momentum transfer. Can you keep the proton intact? What's the chance to keep the proton intact? Well, this we have to contribute to the discovery of the Hadron. Hadron told us roughly about 15% of the time when you large momentum transfer, proton actually can stay intact. So those are the wonderful news. Then people, physicists immediately proposed a multiple process to do this kind of measurement. Say, for example, DVCS, look for electrons scattered of a proton. Proton is the diffracted, but by measuring the final state of photon, then you can factorize that into the GPD, then a generalized Parton distribution of the quark at the lowest order. Then similarly, people propose, what if I measure the meson? Then also, what if I measure the heavy meson, the coconium? Then in that case, it will become the more sensitive to gluons. And also, I said earlier, because exchange quantum number here is a vacuum, if we exchange a vacuum quantum number, not only the color, say spin or whatever, if I exchange that, but QQ bar is not the only state could contribute. You can have a multiple gluon between them. That's related to that we like to have a probe to be localized, so localized that you're pulling the actual parton into your hard collision, you have to pay the penalties. So that means you really like to have large momentum transfer, localize your probe. So this has been, all these process DVCS proposed more than 26 years ago. So there have been a lot of development in theory and experiment. Then in my talk, I would say we even further introduce more new opportunities. So then I just say, how wonderful is this? If you can do that, if you open up a EIC white paper, you will see if I do with EIC luminosities with this measurement, so DVCS, then you can see you can measure the cross-section so well as a function of the momentum transfer T, then in that case, from that to the Fourier transform, then you can extract the distribution in the position space. Then from that, you can construct the effective radius, or say, average transverse position. Then at the different value of x, you can see the radius can be different at the different value of x built in you x values. So that's exactly in the EIC white paper. It's very powerful. EIC is supposed to be able to do that. Then also you do the gluon. If you measure this, then from the EIC white paper, you can see you can get a special distribution of the gluon density inside the proton. So you can ask the question is what effective radius of the proton in terms of its quark distribution or in terms of gluon distribution, which one is the largest? Then that would be very, very interesting or important. But all these nice pictures or predictions, in some sense, is putting by hands. It's modeled with a model of the GPD, with a model of the X dependence, we can simulate it, generate this. But the question is, from the real experiment, can you extract this kind of X dependence? So this is the main focus of my talk. The answer is very difficult for this type of process. Then the question is why? Remember the factorization at the amplitude level, it's over the convolution of the X over the GPD and the short distance Hall part. Then because at the amplitude level in the factorization for exclusive process, then X is the internal dummy variable, it's integrated over. So then special take example DVCS, then amplitude over the proportion of this combination at the leading order. At a high order will be some order wise corrections. Then this quantity is dependent on the C and the T. These are externally measured. External measurement does not directly measure the X dependence. So in that case, then what happened is there is very nice work done by Parton collaboration. So they say, okay, I introduce my GPDs is GPD plus another function so long as that function satisfies this to be 0. So they call that shadow GPDs. In some sense, this contribution, the S function, they can be any function so long as this gives you 0, then you can fit the same data. So that's what they did. They say, okay, I have a different model. Then orange one has a little bit small wiggle over the solid one. Then I can also choose something with a bigger wiggle over the solid one by changing this S. But they both fit data. So that means from the measurement, from DVCS, measure the Compton scattering amplitude. From Compton scattering amplitude, it's not unique. You can extract the GPDs. So that's a challenge. Then they say, well, why this is so different from inclusive process? For years, we study inclusive for like an inclusive DIS. We get a good information on X dependence. Well, example, inclusive DIS, imagine the diagram, you square the amplitude, you have a cut, that's a final state. Because that you will find that your cross sections over the proportional to the X Bilken, it's observable quantities. The range of the X integral depends on the value of X Bilken, depends on the collision energies. So you can become the more sensitive to the X function of the X dependent of the PDF. So that's for the inclusive process. For exclusive process, what you diagram look similar, but actually different because you only observe the photon in the final state. Then this loop momentum is completely dummy, is integrated over. Then so you will find that you are not sensitive to the X dependent, only sensitive to certain moments, depend on the hot part. So now, how can we have, what kind of process observable could be sensitive to X dependent? That's a question we ask, my collaborator and I try to see, is it there a way we can find a new type of process which will actually give us a more direct sensitivity to the X dependent of the GPD, because which is very important for calculating different moments. So then we like to create entanglement between the internal X, imagine GPD, exchange of the QQ bar pair, there is an X in the flow. Then so you want to create the process which can have entanglement between the internal X and the external measurable variables. For example, we propose, as a first one, we propose that the pion to the proton goes to the 2 photon in the final state with a high PT. Then you will find that the transverse momentum from this photon has to flow to the other photon. Then this gluon momentum will be sensitive to the transverse momentum of your observed momentum. So that we're entangled with this momentum flow X. So it will become the sensitive. So then you will find that the amplitude can be factorized. Now you have additional external measurable QT. Then you will have a convolution, then the GPD and the X. Then you have the coefficient function depending on the QT, because the QT is connected with this X that entangled with this X. So when you do the cross-section differential quantity sigma dx dk dqt, you become the sensitive to X. So that's the basic idea. So then we started looking into it a little bit more carefully. They look at the hard part, the 2-photon case.
JianWei, I have a quick question, if you don't mind. So on the previous slide, just to be sure, so X here is not completely fixed by the kinematics, right?
No,
but the
you still need to
kinematics,
get over.
I see, but the kinematics will constrain it better than the standard processes, right? Is
That's
that
correct.
the idea?
Yes, I would demonstrate, because when you change the QT, you sample different part range of X.
I see. Okay.
Yeah.
Okay.
So in some sense, like inclusive, when you change X Billiken, X is still integrate over. But when you change X Billiken, you become the more sensitive to certain range of X. So here is when I change the QT, I become more sensitive on certain part of X. And also this propagator will change me the weighting factor for the different value of X. So when I look at then the 2-photon, of course, you can have situation QQ bar from the GPD, QQ bar from pion. You can have momentum flow from here through this type process, 2-photon from different quark line. In that case, there is a momentum flow Z1. You calculate hard part. Immediately, you find that you become sensitive to kappa, we said before, QT over SDHEP. So that becomes sensitive. But at the same time, you have a type B process, the 2-photon from the same side, they are actually not very sensitive to it. So in this process, in principle, you have sensitivity, but still you have to be careful about the relative side of this too. Then another process probably you are familiar with, then known as double DVCS. If you do double DVCS, you have a virtual photon rather than real photon. Then the advantage of that is that you look at the now this is one diagram by exchanging a virtual photon from the first scattering, then produce a virtual photon decay to dilepton pair. So then you look at this propagator, because X is flow between these two lines. So look at this propagator, you will find that a quick calculation, you will find this propagator is dependent on X. Then have this expression, of course, when the Q2, that's invariant mass of this dilepton, if Q2 go to 0, you go back to the DVCS. But if the Q2 is external variable, then you can change a different weight on this X dependence. You become more sensitive to the X dependence. So double DVCS has a potential to be sensitive to the X dependence on the GPD. Then, but at the same time, you realize double DVCS is proportional to either the 8th power of alpha EM, the 4th power. So it requires a very, very high luminosity to do that. So with these two examples, so we now actually can propose a general process to get to get a GPDs. The process we can have to have two basic requirements. The name we call single diffractive hard exclusive process. It's really typically 2 to 3 is the minimum. You can go to 2 to 4, but 2 to 3 is the minimum hard exclusive process. So in order to see the GPD physics, you need a single diffractive. The hadron come in, diffract to the observed hadron. By exchanging the state, then you need a hard probe. You like to see the quark gluon part, is the particle nature of the quark gluon. So you have a 2 to 2 hard scattering, 90 degrees, in the sense, say you have a virtual state exchange A star by this diffraction, collide with a beam. B can be electron, can be photon, can be pion. Then have a collision, produce a 2 particles in the final state. It's an exclusive process. Once you measure C and the T, you know the SDHEP. But you like to measure the PT or angle between in this frame, then you become the most sensitive to the potentially there is the X entanglement between the transverse momentum flow from here and the relative momentum of this 2 parton in this state. So that's a sort of minimum requirement. The hard probe, you need a single diffractive. Then, so necessary condition for factorization. What the factorization means is suppress the quantum entanglement. So between the different scale. So that here, if you want to see the property of the proton in the diffract, you don't want to have soft gluon interaction between here and here. If the soft gluon interaction between here is so strong, you would change the property of the proton. So that means you like to have this exchange state to live much longer than the time scale for this hard collision. So that means a transverse momentum of the particle you observe, which define the hard scale, have to be much larger than the square root of minus t. This is the factor invariant mass of this state. So that's a minimal sort of necessary condition. It's not sufficient, but we will demonstrate what kind of situation could be sufficient. So this is the process, is a single diffractive and a hard exclusive process. So now then the trouble is of factorization is that you have a soft gluon interaction between any hadron and any hadron involved. These two can be hadron, can be lepton, but gluon can be everyone. So the factorization need to prove, what I have to do is to make sure the soft interaction between these can be either suppressed or canceled or summed to unity. So then with this process, you can look into a little bit detail of this exchange state. Depending on quantum number, exchange state, you can actually exchange the photon, a single photon. Or you can have a Kukuba pair, a gru, or any numbers. So that's a 2 to 3 process. Is the amplitude level, you sum over everything. Well, that has impact because this one is, if you imagine one of the DVCS situation, you can exchange the photons. So that's exactly the beta Hadron type of contributions. Then you can have a Kukuba, you can have a gru contribution. When you square the amplitude, you have interference. You have the square of this guy, interference term. That's exactly what we know from the DVCS. You have a beta Hadron contributions. So then I like have one slide to talk about what situation if you exchange the virtual photon. The virtual photon exchange, because you exchange a single particle compared to Kukuba, the 2 particle, actually you can convince yourself the amplitude for exchange a single photon is actually the leading power, is more important in terms of power counting compared to the exchange of a Kukuba pair. So that means that beta Hadron process compared to, say, DVCS, traditional DVCS, beta Hadron process in terms of power counting is actually more important. But however, of course, we know if you exchange a photon, you pay a penalty of alpha EM. So you have to be very careful to study the interplay between exchange a single photon channel and the Kukuba or even gru channel. So that's very important for the power counting. Then I talked about necessary condition, but also there is a requirement of sufficient condition. It's not that trivial because imagine I have a diffractive by exchange of Kukuba pair, then with a pion coming to produce a 2 photon, only trouble I could have by exchanging virtual gluon, soft gluon between these. The soft gluon between these, if they taken place way before the hard collision taken place, they can break a universality of the GPD or universality of the discrete amplitude, then screw up the predictive power. Well, luckily, if you look at it carefully, in terms of the structure of this propagator, those propagator could have a pole, but none of them are pinched. So if the Kukuba all go into the hard collision, this type of gluon does not give you troubles. But the trouble, especially in the global region, the reason we can have factorization is that when the soft gluon, all the components are equally soft, so then because you have large momentum flow in, so you can only need to keep the one component of soft gluon. So if this is going in the plus direction, you only need the minus direction coming in. So in that case, that's exactly, you can use the water entity to separate the gluon. But what if in the global region, the plus minus momentum actually is much smaller, the transverse momentum? In that case, you cannot neglect the transverse momentum. If this is important, then the transverse momentum can resolve the detail of the pair, then you can break the factorizations. But luckily in this case, it's okay. It's okay. None of them are pinched. They are not pinched in this region, so you can sort of deform out of this region. But there is a DGLAB region. Then the DGLAB region means the one the parton coming is a hit to the hard part, but another one is a spectator. They go to final state, merged with the one coming out of the hard part to become the external state. If you do that, you realize these 2 propagators immediately give you a pinch singularity. They're pinched. That's a trouble. That's exactly, if you remember the Joy-Yang process factorization, you have a 2 hadron collide, produce a dilepton pair, you exactly have this kind of pinch singularity. But the one thing is you only pinch the one side for this GPD side. So that's very important. So what we find that if you have a single diffractive, because this line is not pinched, then we can over the deformed contour plus go to the collinear region. The parton become the collinear, then you can get away from the pinched region. Then that's very, very important because the exclusive process different from inclusive. The proof factorization for inclusive Joy-Yang type process, you need to sum over all the final state cut to get rid of the pole in the 1/2 plane, then deform the contour of the, for the other poles. But in this case, exclusive is nothing to cut to. So you have to rely on other reason to prove the factorization, make sure the pinch singularity will not give you trouble. For in this single diffractive, we find that you can do that. That's good. So because that, with the factorization follow this kind of the procedure, we can start with the collinear gluons. They can be factorized to gauge link. Then the gluon, because in this leading power contribution, then you will find that only the component in the momentum direction, so longitudinal polarized gluons dominate. But because the exclusive process, the whole thing is called a singlet. This can be further factorized. They only interact with the color factors. Then they eventually go into the connector with the original one. Then in the 2 photon case, then this one can be further deformed into become the active parton. So, but because this process, we realized double diffractive process in a hadronic collision will not work in the terms of the QCD factorization for exclusive. So I gave an example. So imagine I do double diffract, 2 hadrons, both diffractive. Then you have this kind of diagram. I exchange gluon from both between the spectator, look like very much like a Joy-Yang diagram, but of course we have an exclusive process here. Then you will find that you have these 2 gluon pinch the say minus component, these 2 pinch the plus component, you are in trouble. We cannot do that. But if you're single diffractive, you can do, again, even this is pinched, then you can deform the plus components away from this global region to make that happen. So this idea actually very much like the one I used with George Sturman way back to prove the pi twistor factorization for inclusive process. You have to treat everything else as a leading twist except the last one. So in this case, the treaty is the one hadron, if it's a multiple hadron, everything has to be leading twist except the last one related to GPD. They can be the gluon connected to hydrogen. So that's a factorized. So what the factorized form for 2 photon case, you have a GPD, distribution amplitude, and the hot pot you can calculate. Then for the most general single diffractive process, as we can follow the same process, the gluon, of course, it can be anyway. It's instead of a photon, I can have a hadron in the final state. So that also works through because the single diffractive nature, we eventually end up with a GPD with a 2 QQ bar or glue channel. So I skipped all the detail here, just say this kind of single diffractive high exclusive process can be factorized. So now we can, because the process can be factorized, can naturally see whether or not I can recover all the process we already know for all these years. The answer is yes. For example, DVCS in this general framework is that the hadron come in, say for the proton, diffract hadron, the proton, then the beam, in this case, the electron. Then the C and the G final state particle, one is the electron, one is the photon. So the lowest order diagram look like this. The factorization formula exactly like you calculate this, give you these 2 short distance hot pot. When you integrate over x, you get at the moment type of x dependence. Then also you can DVMP, you can do in this language, you can also factorize straightforwardly into the GPD and the distribution amplitudes when the hot process is much bigger. So now I want to spend a little bit of time to talk about a new process related to JLab. We can have opportunity to measure it. The process I mentioned of the 2 photon, in a sense, I already talked to the JPOC in Japan. They actually can measure. They have a pion beam, and we are in the process of communicating with the Compass people. Then actually Mark Strickman wrote an email to them, together with me, then to try to communicate the Compass people, use their data to study that. Then the pion beam data. But here I introduce a process with the photon beam. In that case, you look for the final state. You can have multiple type of the final state. You can look for these 2 things of the photon or one meson, 1 photon, or 2 meson, all these things. Then we showed for various process, factorization can be worked out. There is certain processes still there is some constraint, but I'm not going to go into the detail here. It's all listed in our papers. So I want to use the rest of my time to show the phenomenology, the numerical result, and also concentrate on the process which can be measured at the JLab. So for test the GPD, I say, okay, I take the most general GK model, make it a little bit simpler because I concentrate on X dependence, make the X dependence X rho 1 minus X tau by the way the Bessel functions. Then so means I fix area under the curve. Then I try, but if I change the rho and the tau, I don't change the area on the curve, but I change the shape. For example, if I change the different value of rho and the tau, I can vary my X-dependent GPD all over the map. Then you can have a color even, color out. I can choose that. So those are give me the different choice of GPD models. So now I'm going to make a predictions, do the calculation. I start with a simpler case like the prediction pion to the proton to the 2 photon final state. In that case, I have JPOC energy and a compass energy. You will find that if I use different the GPDs, I can really see the difference because those different X dependent. See the difference of this predicted relative cross sections. So that's important. But what I'm going to talk even a little bit more for the rest of is for the photo production because JLab actually can measure. I talked to focus at the whole D. They told me they have data. So what the idea here is for JLab measurement is that we have a photon beam for whole D. Photon beam is linearly polarized. And we have a target, we can have a hadron. In this case, we can actually combine the whole different hole together because they are polarized target from the different hole. So I can have a photon beam on the polarized target, produce a 2 particle 90 degree in this exchange state, the high PT, say pion and also the gamma, and with the diffractive hadron. So then the diagram is like a photon coming with the diffractive the GPD. So you can see the momentum flow X will be entangled with a gluon exchange between these two because the photon come out of the photon. Then in this case, like a pion is going this way. So this is exactly the process will be sensitive. And also because the advantage of our polarization, we can have a target to be polarized. So we introduce a process, had this kind of 2 frame. I define the diffractive frame in the sense as a plane, diffractive plane is a hadron coming, diffractive, the hadron have an angle, that means there is a plane. Then by exchange of virtual state will collide with the incoming beam, in this case, the photon. In this frame, you have a hard collision, 2-to-2 hard collision, 90 degree type of the large angle hard collisions. Then so you will have this PT, and the PT of course is equivalent to the angle theta, because the root S, once you measure C and the T, the S hat is completely fixed. So but PT corresponding to the angle distribution is here. But also because you have polarization, spin direction, you can have angle between these 2 particles, scalar plane and the diffractive plane, you have an angle between them. So then you will construct your measurement depending on this angle, theta and the phi. Then you will write this in terms of unpolarized one with asymmetries, right? You can have a longitudinal and transverse polarized asymmetries, depend on whether beam is polarized or the target is polarized. So then they have a certain angle modulation. So then this is very familiar. People will not having all of us work on the lepton hadron process cities. We take advantage of those things. But for this exclusive process, you can do the same thing. So with this, to skip the whole detail here, this hard part calculation will, because the different observable corresponding to different spin state exchange here, you will be sensitive to different GPD, whether it's H or E or H tilde, the difference between them, the clarity. So you can really have a different observable to help you different sensitivities. So I use the last couple minutes to show a few slides for the plot. First, I tested this shadow GPD. So I imagine I have this is a well-known, say, GK model. The black curve is my GPD. Then, of course, I can add another function, S, X, C, T, so long as S obeys these at the moment equal to 0. Because the moment equal to 0, there must be oscillation between them. So you have a different model, you have a different oscillation. You can have a magnitude could be large and small. Then you will find the for the chiral even one, a tilde chiral odd one. I'll concentrate on H here, not to worry about E for a moment. Then you look for the cross sections. So first I look at the absolute QT distribution, because QT there is a Jacobi part. Then when you hit the edge endpoint, then you will see the huge dependence. And also you can see the angle dependence, which is a little bit smoother. You avoid the Jacobi peak. So then you will have angle distributions. But in terms of absolute normalization, it's not bad. It's multiple picobomb. I talked to my colleagues at the JLab, because of the luminosity they have, they told me you should be able to measure. Then also you take the relative side between the different this is shadow GPD. You can see you can have a 20 or 30% effect. So that's for this absolute cross section. And now I can look at the symmetry, because you look for final state. When the pion, when the photon, you can have a forward-backward symmetry, right? Pion can go to the forward direction or backward direction, because being when is the photon, when is the diffractive hadron, so they are different. So the forward-backward symmetry is not 0. So you will find that at a different QT, then a forward-backward symmetry is very sensitive to the GPDs. And also you can do now that this is unpolarized, just a forward-backward symmetry. Then I can take advantage of polarization. So I can say, okay, my beam is unpolarized, my target is transverse polarized. You can see the symmetries. Then you can see the symmetry, say beam is longitudinally polarized, in this case, linearly polarized. Then also then you have the hadron can also linearly longitudinally polarized. So you can see the symmetry is very, very sensitive on these different GPDs. So that's for this comparison. You notice I keep this H tilde in the same sort of change. The change is consistently together. So then I'm going to even look at the different. The H and the H tilde, they suppose they have a different behaviors change. So try to sensitivity on GPDs. Then you look again, I look for absolute cosine theta and a forward-backward symmetries, and look for spin asymmetries, different combination of spin asymmetries. You can see these curves all over the map. That's good news. That means the experiment data can really help me to pin down the X dependence of the GPD, especially the JLab with those polarized beam and a polarized target. You can have this kind of measurement. So then also in next few years, not necessarily next few months, at least my colleague gave me very encouraging answers. They say they should be able to do the analysis, try to see what we learn. Then we can test the consistency between this measurement and say DVCS, extract from Compton scattering amplitude. You have ambiguity on this shadow GPD part, but with this additional measurement, we probably will be able to pin down what the X dependent GPD. From that, you can measure the calculate the moment, make a predictions on, say, gravitational form factor, or say the angular momentum contribution to the proton spin. So those are all good things. So let me summarize. Then GPD are very fundamental parton correlation functions. In a sense, extracting their X dependence from experimental observable is very non-trivial, because it's an amplitude nature. They come in the amplitude, but full of the opportunities depend on the new observable, because we like to have observable that with external measurable variable, which will be entangled with this internal variable X dependence of the GPDs. Then in this talk, my collaborator in a number of papers, we introduce a class of process known as single diffractive 2 to 3, the hard exclusive process, then to extract the GPDs. This process actually very genetic. We can cover all known existing process in the same framework, and we can understand the proof factorization in much simple way in our approach. Then what I try to conclude that following the pioneering work on GPDs over 26 or more years ago, because when the GPD was introduced and DVCS was introduced. But now after all these years, it seems now we have renewed opportunities for exploring the physics of GPDs and the confined phenomena of QCD. Thank you.
Thank you so much, JianWei, for the very interesting talk. Let's see, we have plenty of time for questions. Please go ahead. You can unmute yourself and ask questions if you have them. Maybe I can start. So I'm certainly not an expert on this subject, but one of the things that you were discussing were these potential issues with factorization, and you were discussing these pinch singularities and then deforming contours. But is there a way in which we can physically anticipate, without necessarily going through the full mathematical calculation, which processes will suffer of these factorization issues? I think you mentioned kind of relationship with Drell-Yan. So can you elaborate a little bit more on that?
Yes, exactly. So when Drell-Yan is a simple example because we're all familiar for last Drell-Yan factorization formula for Drell-Yan process was proposed very early, but eventually full proof factorization, because it's pinch singularity issues, then it took another 20 years after the formula was proposed. Then the reason is that if you two hadron collide, if you have, because this gluon, soft gluon can interact way before the hard collision takes place. Then if the soft gluon interaction is sufficient, is important to change the distribution of the parton inside hadron before the hard collision, that means you lose the universality. The predictive or QCD factorization require all the non-perturbative factorized physics should be processed independent. Otherwise, you don't have predictive power. So those soft interaction will give you this trouble. But why we don't have trouble for Drell-Yan? Because soft gluon is a gauge field, it's a vector field. You have 4 components. Then all the components, soft means all the components are more or less equal. But if they're more or less equal, then when you have a beam coming very large momentum, if the gluon coming with a 4 component all equal, only one more relevant is a component conjugated to the momentum of the beam parton. If the beam in the plus direction, only minus component of the soft gluon be relevant, then that minus component is exactly the direction for the photon to interact with hadron. So that's a longitudinal polarized gluon, or longitudinal polarized gluon. The word that it tells you, although they are important, they are leading contributions, but they have no physics impact. So when you integrate over for Drell-Yan, when you sum over all the final state, unitarity tells you that eventually those affect the sum to unity for the inclusive Drell-Yan process. For TMD thing, it's a second scale will help we be more sensitive on these soft interaction factors, but still can be well defined separate. So the key words is that if the gluon, soft gluon interaction is dominated by the component conjugated to the beam momentum coming, then that direction is exactly in the longitude. Force the gluon, leading contribution of gluon is the longitudinally polarized. So that's what it tells you. That contribution is big, but it's not important. So but the only problem is if the kinematical interaction, force you trap those momentum components in such a like a global region, and then because the collision structure in the Drell-Yan case, the spectator interaction force you, because the pinch singularity, force you to the situation, the longitudinal component actually smaller, much smaller than transverse component, then transverse component becomes important, then you can resolve the internal structure of the incoming beam, then you break the factorizations. So then the proof took 20 years eventually is because unitarity, when you sum over all the final state for inclusive process, it works. So even though I thought about this for exclusive way back 25 years ago when they introduced these, I know there could be a problem but how they cancel, I was not sure. So I could not prove it. Then eventually, I didn't start it, but I had a wonderful student my friends sent to me. Then I talked to him. He got a very interesting from Michigan State. So we talked it. Eventually, we find that if it's a single diffractive, then they can be canceled. The one component, they can be deformed out of it. Then the cancellation is due to a very different reason, because it's exclusive, because every hadron is a color singlet. So it is that reason. It's not the unitary like we normally use to cancel these things. It is the color singlet nature of this hadron to help us to cancel those soft divergence, and also because single diffractive, I can deform the contour out of this global region. But if you do double diffractive, which has some example, people talk about it. If you remember, we go back in the Fermi lab, when initially with the HERO, we discovered the diffractive parton distributions. Immediately, people at the Fermi lab apply the form, assume the factorization. You have a double diffractive, two diffractive parton distribution to predict the cross section for at a Tevatron. They found at that time the prediction is way off the experiment data. They eventually, I remember Dave Soper in one of the CTAC meetings say there is a factorization issues. So when I wrote the paper with my collaborator, actually went through all the literature, we find they've never really wrote a real paper, but in the proceeding, one of the proceedings, he made that statement. So for us now, we realize exactly why double diffractive, this kind of pinch singularity for exclusive process will not work.
So maybe very quickly, so in the case of double diffractive, what's the issue that you cannot, you say you cannot deform the contour because there is too many?
Whenever you have a pinch, that means go to infinity, perturbedly go to infinity, the leading contributions. Then in the global region, means the plus minus component is much smaller transverse component. You cannot neglect transverse component contribution. So the transverse component of the soft gluon interaction can be sensitive to your internal structure before the hard collision takes place. You break the factorization. So for inclusive DI, because the sum over all the final state, you only measure color singlet Joy-Yang pair, then you can prove because the unitarity, when you have a pinch, you have a pole, one pole in the up half plane, one pole in the lower half plane. They can prove then all the up half plane they completely cancel. In the one situation, in the other hadron situation, in the low half plane completely cancel. So then the pole is no longer pinch, you can deform it away. So that's a result where you can prove the factorization for Joy-Yang. Then for exclusive process situation, there is no final state for each sum. There's only one state. That's the hadron you have. So what happened is we find that if a double diffractive, there is a pinch, you just stuck. Then the transverse components become the relevant interaction. The transverse component of soft interaction can resolve your hadron structure before the hard collision takes place. That means you lose the universality of your GPD or the distribution amplitude. So in that case, you don't have factorization. But luckily for single diffractive case, that you can actually, because the plus component is not pinched, you can deform that into in a sense around, make that soft gluon become the active gluon. It's like a part of your beam. So that's a way actually we can show that the single diffractive will not give the harm to this for the factorization proof.
Thank you, JianWei. Do we have more questions?
JianWei, I ask a question. So when you consider photon in 4D proposal,
yes,
there's a hadronic contribution from the photon, right?
Oh yeah. But we're dealing with exclusive.
I know.
Yeah.
I know. But for example, unless you measure everything there, so you do have contamination of the hadronic part of the photon. That could cause problem, right?
If this by definition we do the exclusive means that we measure everything.
Okay, that's the exact point. So you measure everything there. So that means you also have to measure finite state electron. So here the question, a related question. I looked at actually a couple of years ago. I looked at the in particular for the two photon exclusive production. There is a significant beta hadron contribution.
Absolutely, that's actually leading very big contributions.
Yeah. So in your proposal for her D,
is a one photon, one pion.
No, you could also have this beta hadron. So in the sense that one of the photon in the final state coming from electron.
Yeah.
So that could also contribute to the process.
Correct. If you do the charge, you do the transition GPD, then you can avoid that one.
What do you mean transition?
If I measure the photon with the pi plus in the final state.
Yeah. No. The photon. Okay, so it's the same process, right? You measure the photon, the pion in the final state.
Yes.
What I'm trying to say is that photon could come in from electron.
Oh, sure. That part is I rely on my experimental colleague. They can say they can measure pretty good on the exclusively photon. We actually have another process. Is instead of photon pion, look for the two hadron final state, the two meson final state. There is a little bit complication of factorization. If the short distance hopper is a strictly hop process, single point, then it's okay. But when you produce a two pion final state, you can have a situation so-called Landsov mechanism. You can have in the so-called hopper, a factor is a 2 point. Then there is a distance scale between. You can integrate it over. That part, there is a paper by Shannon Lee and George Sturman a long time ago. They say the Sudakov can help suppress that problem. As far as factorization concerned, if I have a soft gluon attached to the state in between those two local points, then my factorization will break because that scale is not the hard scale.
Okay, JianWei, so I'm just comment on that. So I think you should consider that beta hadron contribute to the photon plus pion. So, so I'm just put an analogous. So if you have two photons in finance, I know that Mark Steele had a paper show that beta hadron contribution actually dominated for this two photon exclusive process. So this could happen for your photon plus pion as well.
Yeah, if I mentioned earlier, if I do the pi plus, I can avoid that, pi plus or pi minus. Do the transition.
No. It's the same process you're considering the pion plus photon in the final state. What I'm trying to say is that photon could come in from electron.
Oh, photon, my final state is a final state, the pion, the electron to the photon.
So you have pion plus photon in the final state, right?
Yeah.
So
I have a direct photon, larger angle, 90-degree direct photon.
Yes, but the photon could come in from the electron as well.
Which electron?
Your incoming electron beam.
I don't have incoming electron.
I know. So that's why I'm saying that in Hall D setup, so in order to really get this exclusive process, you need to measure everything, right? You need to measure the final state electron, and also final state photon and the final state pion, right?
You're absolutely. I was told they can have a pretty good photon beam because electromagnetic field will turn the electron away.
I understand that because this is really exclusive or real process.
Correct.
I believe in the Hall D, it's definitely dominated by the photon flux, right? But there's still a chance that I mean, if you electron, you have to measure the electron to make sure that it's a real photon process. Right?
But the 90-degree, I require, this is very different. I require the final state pion and a photon are very large PT. So chance for an incoming electron to go to the large angle PT photon is very, very small.
Oh, that's okay. So I just comment on this analogous to photons. So it's the same thing. So it's simple kinematics.
Okay.
Yeah, anyway, so
we can talk in details.
Sure, no problem.
Yeah, I talked to my Hall D colleague Justin Stevens, that he has been helping me to see how do you measure them, because the high PT is very, very important.
Sure.
Thanks, Feng. Do we have any more questions for JianWei? Okay, I don't see any more. Again, thank you, JianWei, for this nice talk.
Yeah,
Okay.
JianWei,
Thank
hey.
you. Nice to see you guys. Then,
Hope to see you at Berkeley soon.
I missed what you say, Fan.
Hope to see you in person at Berkeley.
That's right. Absolutely. Yeah. I wish I could be there because you can see your question. If I were there, we would be discussed much more, much better.
Okay, think
Yeah.
about it.
All right.
Yeah.